Welcome everyone to my recorded presentation. The title of my today's presentation is Handling Uncertainties in Balancing Long-Term and Short-Term Objectives in Water Flooding Optimization. So let's start with the introduction. And closed-loop reservoir management, as shown in this block diagram, consists mainly of a reservoir model, and then it updates this reservoir model with the help of measurements, as shown in this red data assimilation loop. The blue optimizer loop aims to optimize the economic life cycle performance of oil reservoir. I can safely place my research in this optimizer loop. Let's see what are the challenges in this model-based optimization. One of the major challenges is the uncertainty. Consider this reservoir model. You have a permeability field, but the real knowledge or the true knowledge of this true permeability field is highly unknown. So you can come up with different other realizations, and you're still not sure that which of the realization is the true one. Another source of uncertainty is the economic uncertainty. Changing oil prices is the key source of this economic uncertainty. These oil prices changes with time, and they cannot be precisely predicted. So if I want to summarize my work in 2 lines, I would say that I would be working on decision making, which is the model-based economic optimization, under this geological and economic uncertainty. Now, how am I going to achieve this target? Here's the recipe. I'll start with the definition of the model-based optimization, and I'll compare it with the conventional reactive strategy. Then I won't use the uncertainty in this model-based optimization, and we'll see the effect of uncertainty. Then I'll talk about how we can handle this uncertainty, and also give some previous work that has been done before. Then I'll move to handle the geological uncertainty only. I'll believe that in this case, the economics are known and well certain. I'll first introduce and talk about the averaging approach that has already been done, and then I'll talk about a mean variance approach. Then I will extend this work to the case of economic uncertainty, and I'll do the same treatment with the economic uncertainty, considering that the geology is certain. And then I'll end up by giving some conclusions and some future directions. So, like every optimization problem, this model-based optimization has a cost function. It is a financial measure called NPV. It is net present value, so it is the net value between the revenue that we earn from the oil production subtracted from the cost involved in water injection and water production. It's also a present value, so it considers the interest rate or discount factor. And important thing that it's a cumulative cost, which you can see here with the capital K, which is the life cycle of your reservoir. It's a highly non-convex problem. There are different ways to solve that. I use steepest ascent line search scheme to solve this optimization. And I use gradients, which are obtained by solving an adjoint equation. I compare this with the reactive strategy. Reactive strategy simply means that inject it for the maximum rates and simply shut in the production wells when they are no longer economical. Then I did this experiment using the egg model. This is a 3D synthetic reservoir model, and more detail you can see in this paper. So I did the experiment. I used the nominal. I'm calling it nominal because there is no uncertainty involved in that. And then I compared it with the reactive one. What I get is something like that. What you see on the x-axis is the time. So the time goes to 3,600 days, which are basically almost 10 years. On y-axis, you see the NPV in US dollars. The blue curve shows the result of the nominal optimization. I got the nominal input, I applied it to the system, and I get this NPV time evolution. The reactive strategy is shown in green. Now, the first observation is that the long-term gains, as per the NPV says, are higher. But we also observe that this long-term optimization does not address the short-term gains. So for example, if you're a manager, and if I come to you and say that, hey, see, we can earn $2 million more at the end of the life cycle after 10 years, but we have to compromise almost 30 million in the beginning. What would you say? You'll say, are you sure about that? And I'll reply, no, not really, because I have uncertainty in my models. The economics are also uncertain. And then you definitely prefer the reactive one. You'll show more confidence into that. Now, what I should do to give more confidence on the model-based strategy? And the second thing is that what are the indicators that will reflect this confidence? The first answer to the first question is straightforward. Include uncertainty in your optimization, and then it will give confidence. But the second question has different perspective about the indicator of confidence. High short-term gains is one way to give confidence to your strategy. Now see an example here. Let's consider I have two strategies. Let's call it strategy A and the strategy B. And this is the result of those strategies in terms of NPV time buildup. And we can see that they achieved almost the same NPVs at the end. The only thing we know that this NPV that we have achieved is uncertain. Now, among the two strategies, which one will you prefer? A or B? Your answer will be B. Why? Because it has a higher short-term gains. And that basically reflects your implicit attitude into not running into risk of losing revenues tomorrow. And you give high confidence onto the strategy. Another important thing is that the short-term gains are important, high short-term gains are important because when the time goes, your uncertainty becomes more profound, the negative effect of that uncertainty becomes more profound on the strategy. So you really want to increase the rate of oil production or want to have the high short-term gains to have better confidence on your strategy. These two questions have been addressed in literature, but in a different way. So Hayes introduced a robust optimization scheme by doing an averaging. So he considered an ensemble of reservoir models and did some averaging on that. This approach incorporates the uncertainty, but it does not have the mechanism to basically reduce the sensitivity of the solution, the optimal solution to the uncertainty. We will see this later in our presentation. Another approach that Hayes introduced was a hierarchical approach, in which he changed the criteria into a multi-objective one, which consists long-term and short-term, and used the highly discounted NPV to basically put more focus on the short-term gains. It was a nice approach, but it indirectly tackled the problem, and it does not consider the uncertainty, which was the main core reason of this risk of losing the revenues. Raoul extended this approach to robust, hierarchically includes an ensemble of the geological models into that and turned it into robust hierarchical. We also did some experiments, submitted this work, where we include the economic uncertainty in this robust hierarchical framework. But still, this robust hierarchical also does not aim to reduce the sensitivity of the solution to the uncertainty. So we've come up with the idea that this changing of the criteria that we saw in the hierarchical one is an indirect way of steering the solution toward desired direction. So we think that the solution should change, not the criteria. So because under the presence of uncertainty, we should not treat this criteria, but we should focus on changing the solution in the desired direction. So it's obvious to now include the uncertainty in the optimization framework. And we look into the basic question, or the major question, that can by explicit handling of the uncertainty, the balance between the long-term and short-term be naturally obtained. So it was a good point to move towards the robust optimization scheme. Now, dealing with the geological uncertainty can be considered into two different ways. The first thing is really reducing the uncertainty by using measurements. The other thing is to reduce the sensitivity of the solution to the uncertainty. Now, from now on, when I say reducing uncertainty, for the sake of simplicity, I would mean the second part means reducing the sensitivity of the solution to the uncertainty, because I'm not using any measurement. So what Hayes did, he considered 100 realizations, an ensemble of 100 realization of egg model. So like, for example, see the 6 randomly chosen realizations. And he considered an averaging cost function, objective function, which is basically the average of the NPVs, individual NPVs coming from all the 100 models. And he took the average. We repeated the same experiment. And then the results that we get is something like that. So let's understand this curve one by one. What you see on the x-axis is basically the NPV. And then on y-axis is the probability. What you see in the red curve is basically the robust strategy that we obtained, one robust strategy that we obtained by doing the robust optimization that I introduced. In the last slide, I obtained a robust strategy. I applied it to the whole ensemble. I obtained 100 points, and I draw of it a distribution into that. I did similar with the reactive strategy, which can be seen in the green curve. The 100 blue curves are basically the 100 nominal strategies that I obtained from each model. And then I applied each strategy to all ensemble, and I obtained 100 times 100 NPV points, and I draw 100 probability distribution curves to that. And you can see that on average, the robust strategy performs better than the other strategies. But the point that I was mentioning before is that the uncertainty in the parameters are now mapped to the uncertainty in the distribution. So if the uncertainty in the parameters are high, we will observe a higher variance in this robust optimization curve, which reflects that it does not particularly aim to reduce the sensitivity. We were interested in the time buildup. And then that's the time buildup. And then what you can see in the red curve is basically robust strategy applied to 100 models in the ensemble. The blue curves are basically the nominal strategies applied to themselves. And then the green one is the reactive. The maximum and the minimum NPV values will form this tube. And you can see that the short-term gains, even in this robust approach, is not improved. This is probably because of the reason that we have not properly handled the uncertainty. We have not reduced it. We have just incorporated it in the optimization framework. So we decided to move further and consider a mean variance portfolio approach introduced in this paper. What the idea is basically idea coming from the portfolio optimization, where you want to maximize the return, but you still want to keep the risk minimum. Here in this work, they consider the return to be the average outcome, the average NPV, while they quantify the risk in terms of the variance of the NPV distribution. And they did it for the geological uncertainty. And here is the objective function. So that's the mean minus some penalty terms on the variance times the variance objective. We implemented it with the 100 egg model realizations, and what you get is something like that. The red curve is basically the robust strategy, and the green curve is basically the reactive strategy, while the other curves that you see are coming from the mean variance strategy with different values of gamma. And you can see that when we increase the penalty on the variance, the return decreases, but the variance, which is the risk, reduces. But we were interested in the time buildup. And that's what we observe here, that when we change the gamma in the mean variance objective, if we put more weight into the variance, we want to reduce the uncertainty more, we can see that we observe a higher time buildup with dealing with the geological uncertainty, and then which is evident from these curves as well. So the red curve is robust, the green is the reactive, while the other colors that you observe here is with different values of gamma in this mean variance optimization. That was about the geological uncertainty. Then we considered, then we move further to consider the economic uncertainty as well. Here we use just one model. So now the first question arises that how to incorporate these changing oil prices into optimization framework. One obvious choice was to consider the average value. The other choices are the extreme cases, that may be worst case or the best case, whatever you prefer. Another approach is to consider the set theoretical approaches, because in literature you can find the relation between the risk that you define and the uncertainty set that you build. But probably we didn't look into that because I thought that this could be much more fancier considering the complexity of the problem that we are talking about. So, but before considering making any choice, we just had first feel of how the economic uncertainty will react in this or will behave in this optimization problem. So we considered some time oil changes profile. It's just the exponential increase that you can see here in this graph is the oil price versus the time. And then we observed what we intuitively think of. So what you can see that when the oil prices are changing, so so the first curve that you see, the red curve, is basically has a very high oil price at the end. Optimization did what we think it will do, that it will put more, it wants to earn more at the very end when the oil prices are very high. And then it shows a very direct effect of changing oil prices on the optimization. So we thought, let's include this economic uncertainty in a way that we have included the geological uncertainty. So we can see we generated this 10 ensemble of changing oil price. There are different ways of basically generating that. We consider a very simple way of generating that, which is the ARMA model. We just wanted to make our point clear. So, and then we consider the same averaging approach that we have dealt with the geological uncertainty, considering the 10 ensemble shown in this figure of changing oil prices. And then we also implemented the mean variance approach with this case. And that's the objective function of that. What we observed, or what we get, is basically what is shown in this graph. The red one basically shows the robust strategy, the outcome of the robust. The green one is basically the outcome of the reactive strategy, and the blue one is one outcome of the mean variance strategy with a particular choice of gamma. The very first observation is that, see the width of these tubes. They are the width is very high. The reason is that the effect of uncertainty, the economic uncertainty, is very high in these optimization problems. The second thing you observe is that in the mean variance, as it has as an intrinsic way of reducing the uncertainty, you can see that the short-term gains are high in case of mean variance. For the sake of clarity, I'm showing here the mean values of these tubes here. Now you can see the red one is the robust one and the green one is the reactive one. And then the other three curves are coming from mean variance with different values of gamma. And you can see that in the mean variance, we are able to push up the short-term gains a bit higher. And now we have more confidence in terms of the strategy. Now, we thought that, okay, it may be the reason that you can think of that we've fabricated or we just choose the oil prices as to get these good results. But then to counter this argument, we consider we did some more experiment as well. And here I'm showing the oil price scenarios where the average is going high. So previously the average was going low. So in this case, we can see that robust, which is the averaging approach, showing what we were thinking it to be. That as the oil prices are high at the end, it wants to earn more, or it wants to improve the oil production at the very end. And this is shown in the red curve. And the green curve is again the reactive one with the same oil price scenarios. But now you can see that the mean variance for different values of gamma still work very good in this case as well. And this leads me to the conclusion of my work. So we have seen that the effect of economic uncertainty is more dominant in these model-based optimization that I've shown compared to the reactive one, or compared to the geological uncertainty one. One possible reason is because of the nature of these uncertainties and the time-localized effect of these uncertainties. You might be thinking throughout this presentation that NPV is a long-term objective, and then how come you include the short-term objectives without explicitly considering it, without changing the discount factor or doing something like that? One possible reason of the good results that we obtained with the mean variance by reducing the uncertainty is maybe the time-localized effect of these uncertainties. We know that the economic uncertainty is dynamic in nature. It changes with time. While the geological uncertainty is static, but it's still, because of the fluid flow, you still observe in future it has some dynamic behavior as well. And then because of this time-localized effect, you may induce higher short-term gains in this long-term optimization as well. And we observe that the economic uncertainty has higher effect, maybe because of its dynamic nature in this optimization. Another important thing that we observed was the gamma parameter in this mean variance optimization. In the typical portfolio optimization, this gamma parameter is used to select the portfolio with a particular risk and a particular return. So it depends upon the investor that how much risk he prefers on how much return. Here, it plays another role that it helps you to balance the short-term and long-term objectives, because you have to compromise something on the long term if you want to achieve something in the short terms. And this gamma parameters proves to be an explicit parameters to tune this or to balance this short-term and long-term. Another future direction could be that better handling of uncertainty, because variance is just one way of dealing it. There are some other ways, there's other risk measures, for example, percentile risk measures, for example, value at risk, VAR, or conditional value at risk, or some other, or standard semi-deviation. They are the risks which are more common in economics now. And then including that, we may improve our results even further. At the end, I want to thank the sponsors. And this is the list of references. And thank you very much for attending my talk. Thanks a lot.